All right, so thank you for coming out tonight. My name is Mike Siegel. I work for the Swift mission. I'm going to tell you a little bit about that. But what I'm mostly going to be talking about is other science we do with this amazing instrument. So just, a lot of you are probably familiar with this, but it's always worth going over. Swift is an Explorer mission launched in 20th November 2004 during a Penn State football game, as a matter of fact. And we've been in orbit for 14 years, so we're close to getting our driver's license. It is a mission designed to solve what was then the mystery of what are gamma ray bursts. And these are, as we have figured out over 14 years and studying over 1,000 of these things, these are the largest explosions in the universe, basically the birth pangs of black holes, either from the explosion of very massive stars, over 10 times the mass of the sun, or the merging of two neutron stars into a black hole. Now this is the cartoon of what Swift looks like. And it's got three instruments. You've got this funny hat-looking thing called the BAT, the Burst Alert Telescope. And what that does is it scans about a sixth of the sky at any one time, looking for flashes of gamma rays. And it doesn't look like a telescope, because gamma rays and X-rays are hard to focus. They're very high energy, so if you just put a mirror out there, it's just going to go right through it. What this is what we call a coded mask. It's got little holes in it, and the gamma rays come in, they diffract off those holes. They create a little pattern on the detectors. Because we know the pattern of holes in the mask, we can decode that and get where the gamma rays are coming to very high precision. And Swift is automated. It's not an acronym. It's called Swift because it moves very swiftly to respond to automatically respond to the detection of a gamma ray burst and repoint these instruments, the X-ray telescope and the UV optical telescope. These are more traditional telescopes, what you think of when you think telescopes. These are narrow field instruments that study the gamma ray burst. And we follow it for hours, days, sometimes even weeks. So this has been, as I said, in orbit for 14 years, but gamma ray bursts only happen a couple times a week. And we study them very intensely. It's still our bread and butter. But a lot of what we do is the science between the bursts. One of the things I like to say about astronomy is that if you build it, they will come. If you build an instrument that is capable of doing science, when you're studying even a very specific issue, people will find new and interesting things to do with that instrument. Swift has these amazing capabilities. It can respond within, we can send a request to the telescope and have it repoint within minutes or hours to a new source if someone alerts us to something interesting going on. It gets simultaneous X-ray and ultraviolet imaging, which only AstroSat as a new instrument can do. And it has a very wide field. And so people keep finding new things to do with Swift. We have a very active target of opportunity program where people go to our website and request. We get over 1,000 requests a year. We have GI programs where people propose big programs. And we do a lot of science. Basically, if it's not the sun or the moon or a planet, we look at it. That's the way it works. And so you can see here, we do comets. Earlier this year, we had a really spectacular result where we measured the rotation of the comet and showed that it had slowed down dramatically because of ice eruptions on the surface that changed its rotation. We studied nearby galaxies. This is a survey of the Magellanic Clouds. I'll talk about more of that in a second. We studied asteroids. We showed the collision of asteroid Sheila with another asteroid. We're doing a survey of the nearest several hundred galaxies to learn things about how stars form and how dust gobbles up the light from those stars. This is a very lovely picture of the Andromeda galaxy, one of the nearest galaxies. We just graduated a student who did her dissertation studying the star formation going on in here. And this is not an image from Swift, this is a cartoon. We were part of the really spectacular discovery last year of the electromagnetic counterpart to the LIGO detection, to these two neutron stars colliding. When that went off, there were hundreds of people and dozens of telescopes that surveyed the sky immediately looking for the counterpart to that gravitational wave. It was first reported by Sarah Tololo, but we also detected it in Swift, and we detected it in the ultraviolet, which was not expected, and we learned a lot about this event of these collision of two neutron stars from Swift. So we basically do everything when we're not looking at gamma ray bursts. And that's how Swift operates. We have this amazing team of science planners that take all these requests and somehow get us to observe almost all of them in one day. So we're going around the sky, and while we're looking at these targets, say somebody wants us to do a comet, we're looking at that comet, BAT is meanwhile surveying a huge area of sky looking for a flash of gamma rays. And if it detects a gamma ray burst, it alerts the telescope, we drop whatever we're doing, we chase after the gamma ray burst, and when it's gone, we go back to our regularly scheduled programming. And so this is what we do, the science between the bursts, what we do when we're not chasing a gamma ray burst. Now, what I work on are what we call hot stars. These are stars, depending on who you ask, of over 7,000, 10,000 degrees. The sun is about 5,800 degrees. Hot stars are something you really are sort of the last frontier of stellar astrophysics. Most aspects of stars we understand pretty well. Now, that might cause people who study stars, like Howard over there, to faint, but when they wake up, they would agree that we mostly understand stars. But hot stars we don't really understand as well as we should. And there's a very specific reason for that. Cool stars are, a few thousand degrees, they give off most of their light in the infrared. You can study them from the ground. As a star gets hotter, it gets bluer. It starts emitting bluer and bluer light. When they get up to the temperature like the sun, they're emitting a lot of their light in the optical, so you can study them from the ground in the optical. Once they get up to 7, 10,000, 20,000 degrees, they're putting out most of their light in the ultraviolet. And the atmosphere blocks ultraviolet light from getting to the Earth. Now, I guess that's a good thing. It's the reason you can't go outside and die of a sunburn on a cloudy day. But if you're an ultraviolet astronomer, it's a little annoying. And so space instruments are how we study these. And this is a mosaic we did of the Magellanic Clouds, one of the nearest galaxies to our own. There are about 1 million ultraviolet sources in there. Everything you see in there is an unusual star. Hot stars are rare. It's one of the reasons they've been hard to study. They usually are either stars like the sun, what we call main sequence stars that are burning hydrogen in their cores, but much more massive, 10, 20 times the mass of the sun. They don't last very long. The bigger a star is, the more furious the fires within it burn, the shorter the lifetime, so they don't last very long. And they're rare to begin with. The other kind of hot star are stars in phases of stellar death. When stars are dying, they go through various changes, and at times they become extremely hot. And so this is a good way to study these hot stars. This up here is 30 Doradus. It's one of the most active regions of star formation in our nearby universe. It has some of the largest and most massive and most ultraviolet bright stars that we can study. So we learn a lot about how stars form and a lot about hot stars by looking at that at 30 Doradus. So this is a very interesting region of space to study. And this took us not over a few months. It's about a couple of days worth of observing. There's about 150 images that we mosaic together. And it's one of the most spectacular images that UBOT has produced. And we just got funded to do a study of this to learn more about hot stars. Now, my particular interest is in what we call R Lyrae stars. These are a very classical target to study in astronomy. Certain stars, at points in their lives, become unstable. Not unstable in the explodey kind of way, but unstable in the pulsational kind of way. A star like the sun settles down into what we call equilibrium, where the energy that's being put out by its core from burning hydrogen into helium is balanced by the energy coming out from the surface. So the star is very stable. Our sun will undergo very slow changes over its 10 billion year lifetime. It will mostly be stable. But there are certain kinds of stars where they're not stable. Instead of hitting that equilibrium point and staying there, they sort of bounce around it like a pendulum, getting hotter and cooler and never quite getting into equilibrium. And they pulsate in a very regular cycle. This is what we call a Hertzsprung-Russell diagram. It shows where stars end up. So brighter stars are towards the top, fainter stars are towards the bottom. Hotter stars are on the left, cooler stars are on the right. And there are various sequences for where stars end up. This right here, cutting through various kinds of stars, is what we call the instability strip. That's where the stars have the right temperature and the right brightness to become unstable. All the stars within this area pulsate. They range from pulsations on the scale of hours to pulsations, up here are what we call the Cepheids that we use to measure distances. They pulsate over days or weeks. R Lyrae sit down right here. These are very old stars. in the phases of stellar death that get to this point where they are unstable and start to pulsate on a regular period. Now, these were actually discovered in the late 19th century. This, and I apologize for the quality of the image, hopefully you can make it out. This is a photographic plate taken by Pickering. And what he wanted to do, he was taking images of the sky, and he had a whole bunch of women working for him called computers, who then processed the data and got the results out. And two of them, Annie Jumpkinnon and Henrietta Swan-Leavitt, made two of the most fundamental discoveries in the history of astronomy based on working on these. This was another discovery. What he would do was he wanted to see how stars changed with time. So what he would do is he would take a picture of the sky, then turn the tracking on the telescope off, close the shutter, and the sky moves a little bit because the Earth's rotating. Open the shutter again, turn the tracking on, take another picture. Close the shutter, turn the tracking off, let the stars move a little bit. So what you see are these images over and over again. Each one, he imaged here, closed the shutter, imaged again. He's getting a series of images all on one plate. Now, most of the stars were stable. They stayed the same. This is one star up here, and you can see it doesn't change very much. This was the big breakthrough. This star started out bright, then almost disappeared for a couple of hours before coming back. This plate spanned about 8 hours of observation. And so this was the first discovery of a variable star, and they went on to discover more of them. These stars change very dramatically. The most intense, they pulsate with periods of maybe 6 to 24 hours. The most extreme, let's say the sun were in our Lyrae, if you got up in the morning, at 6 a.m. it rises above the horizon. Within a couple of hours, it would be 10 times as bright as it started out with. And then would slowly fade throughout the day, and then at sunset start rising again. These are very extreme objects. What's happening is two things going on. One, the star is physically expanding by a couple 100,000 kilometers in the space of a couple of hours. It's swelling up and shrinking down. Swelling up and shrinking down. As it does that, it gets brighter because the surface of the star gets larger. It's also getting hotter. The star goes from, say, 5,000 degrees to 6,000 degrees. So you're talking about something the size of a star changing that dramatically in the span of hours. It's a pretty amazing feat. Now, if you want to study, and I apologize that there was no color for this logo that worked out and didn't look awful. If you want to study our Lyrae, you go to globular clusters. This is the globular cluster Messier 3, and it's sort of the Rosetta Stone for studying these stars. It has been the most studied. We have over 120 years of data on this cluster. It's been studied by every instrument, and it has several hundred of these variable stars. So if we showed a movie of this, you would see this twinkling of these stars, not from the sky, but from the stars actually changing. And this is what we use as basically our baseline. Every time we study stars, or our Lyrae stars, we start out with M3, because that's the most well-studied. That's the baseline we use for comparing to everything. Well, when I started with Swift, the thing I discovered was basically no one had done these stars in the ultraviolet. There were a few little studies of the occasional star, but no one had studied hundreds of them like we do in the optical. And this was a huge gap in our knowledge, because there's as I'll show you in a minute, there's a lot we can learn from these. And the reason was, you have to go above the atmosphere, and a lot of the instruments weren't well suited to this. The Hubble Space Telescope could do this, but it only images little patches of sky. It wouldn't image an entire cluster. Other instruments, they didn't have the resolution. They would be very blurry here. Swift was the first instrument that could really do this on this kind of scale. And so this is where you go when you want to study our Lyrae stars. Now, this is what we call a light curve. It shows how the brightness of a star changes with time. And this is showing two kinds of stars. This is one of the stars in M3. You can see it pulsates, gets gradually brighter, and then shrinks down, gradually brighter, and shrinks down. And then this is another kind, and this, we put these in terms of days, so this is about a third of a day. It takes about 8 hours to go through that cycle. This is another star that goes up much more dramatically and then slowly fades. Much more dramatically and then slowly fades over the course of about 12 hours through a full cycle. What's interesting about the ultraviolet is these pulsations are much, much stronger in the ultraviolet than they are in the optical. They can go, in the optical, you're talking about something increasing its brightness by 5 to 10 times. In the ultraviolet, they can increase their brightness up to 1,000 times in the span of an hour. You look at this one, this little piece here where it's getting really bright, it's swelling up and getting hot. That takes only an hour, hour and a half. So it's a dramatic change in this cluster, in this star, as it swells up 100. The outer part is going out at a couple 100,000 kilometers. Temperature is changing dramatically, just huge changes. The reason these pulsations are so powerful in the ultraviolet is because when they're cool, when they're at 5,000 degrees, those stars don't put out a lot of ultraviolet light. When they get up to 6,000 degrees, they dramatically increase the amount of ultraviolet light they're putting out. And so these pulsations are really huge. And the effect is to amplify everything that's going on in the star. Things that we would study in the optical are much larger effects when you study them in the ultraviolet. Just to show you one thing, I'm going to focus right here on when the star is at what we call minimum light, when it's at its faintest. I'm going to blow that up a little bit. And again, apologize for the blurriness. So the star is fading, gets to its bottom, and it sort of bounces around a little bit, hiccups a little bit, and then comes up. This is not just some random variation. This is real. This happens in these stars. What we are seeing is the effect of shocks inside the star itself. What happens is the star has swelled up and it's contracted. Those outer layers of the atmosphere, though, come in very, very slowly, drift down. While they're drifting down, the inside of the star is cooking up a new pulsation. It's warming up, starting to produce a lot more energy and heat, and that causes the interior of the star to start expanding. Eventually, this outside of the star and this interior of the star crash into each other, creating a shock wave. The star sort of brightens a little bit, fades, and then eventually that heat mechanism in the core of the star overwhelms the atmosphere and it swells up again, getting 10 times as bright. So this is sort of the tremor right before the earthquake. A little variation in the star where it sort of shudders a little bit as the interior is mixing around before it finally goes up into this pulsation cycle. And this is just one of many little points in these light curves where we find these things, these little variations that show, expansions of what's going on in the interior of the star. And again, normally to see this sort of thing, you would need to take thousands of observations or have a really, really precise instrument like Kepler. In the ultraviolet, you see them really easily. And this is not ideal. This is just a random star and a cluster we did. If you picked out really ideal stars for this, you could get much more information. And so we're learning, thanks to Swift, a lot about what goes on inside these stars. What is powering this mechanism that makes these stars change so dramatically over such a small period of time? And so I like to say we're using 21st century technology that was designed to solve a 20th century problem to go back to 19th century astrophysics. Still looking at the same things Pickering was 120 years ago, but now looking at them with much more precision and getting much more information out of them and learning so much more about what goes on inside stars. And the thing I want to emphasize here is I've shown you just a little sliver of the science that I do, which is a little sliver of the science that Swift does, which is a big sliver of what it overall does. This instrument is amazing. If I wanted to talk about all the things, I think they wouldn't want us past closing time, but you get the idea. There's so much that this instrument is capable of, and so many ways that people invent to find new and exciting things to do with it. So again, if you build it, they will come. If you build an instrument that is capable of doing all kinds of cool science, and you surround it with a team that is capable of adapting to the new science that needs to be done, you can make some amazing breakthroughs, such as revisiting an ancient stellar problem that we need to solve, and getting new insights into what's going on. And so thank you very much.
What's the future of Swift? Is it?
Swift has no, he's asking what the future of Swift is. So NASA's instruments undergo what we call senior review. It used to be every 2 years, now it's every 3 years. NASA has all their functioning telescopes submit proposals for what they want to do for the next 3 to 6 years. And then a gang of worthies looks over it, decides which should get funded. And based on that, we either continue or are canceled or pared down. So far, with one exception, Swift has finished #1 in every senior review. The reason is because we have a very small team and we do an enormous amount of science. So the science to cost ratio is very good for NASA. We have another senior review coming up. We have more we want to do, especially with following up LIGO triggers and other instruments. The earlier talk about neutrinos, we've been following those up too. We haven't made any, we were part of the discovery he was talking about with the Blazar, but we're still going to be following up those. So there's a lot to do in the next 3 to 6 years. So we'll see how they fund us. Operationally, everything's working. We don't have any fuel, so there's no expendables other than the ultimate expendable, which is money. The last projection is that our orbit should stay in the sky until the 2030s. I hope I'm lucky enough to still be doing astronomy in the 2030s. But right now we're in a good shape.
So I assume it should be reaction wheels, right?
Yes, we use reaction wheels to repoint.
And when no one's actually looking at it, is it slewing, auto-slewing when it sees something?
No, we have hundreds of targets, dozens of targets we do during the day, so we're always looking at something and moving between those. And that's good for gamma ray bursts because it means that BAT is constantly looking at different parts of the sky looking for gamma ray bursts. And then when it finds one, we drop everything we're doing and chase after that. So we do a lot more slewing than most instruments do. We aren't as precise as other reaction wheels, which is why ours haven't worn out so far. But that is what we use.
Do they run slower? Is that the whole point?
We use a lot less force when we use them. So that means we don't point as precisely, but we move faster.
Gotcha. Thank you.
Yep.
How big is it? Can you give a sense of the scale? Of the
How big is it? Swift is, I think, about the size of a minivan. These telescopes have to be small because you can only put so much payload on the rocket. So it's not that big. The AoT telescope is a 30-centimeter telescope. That's smaller than a lot of amateurs have in their backyards. The main advantage is that it's a really precise instrument and it's in space. But this is, we use a lot of, one of the ways we kept costs down on this was to use a lot of off-the-shelf technology, stuff that had been proven on previous missions. A lot of the things like the mirrors inside the X-ray are spares from a previous mission. The UV optical telescope is basically a copy of what went on with the XMM, the X-ray monitoring mission. So that's one of the ways we kept costs down, but it's not a very big telescope. Its main advantage is how well it is planned and maintained and that it's in space.
So you focus, like the gamma ray burst, you focus like you do in the Chandra, the supercentric metal plate?
All right, how do we focus with the gamma ray burst? The X-ray telescope uses those what we call grazing incidence mirrors, where the mirrors are sort of angled and gradually deflect the X-rays to the detector, because X-rays don't like mirrors, they just will go right through them. The BAT, as I said, uses a coated mask, so it doesn't even reflect them. They just diffract off that mask, and we can decipher that into a position.
So it is like Chandra.
Yeah, and with the X-ray telescope is similar to Chandra, yes.
Any other questions?
Some of the structure you saw in the intensity curve, can you elaborate on some of the things you learned from that substructure?
One of the things, it gets very technical very fast with what we learned there. What have we learned from some of those little variations in the light curves? One of the things we're exploring now is, so the interior of the star heats up. At a certain temperature, hydrogen stops being a molecule and becomes an atom, it ionizes. We're learning, one of the things we learned is that where that occurs is not as uniform with these stars as we thought it was. That people thought that ionization occurred at minimum light for all of them, and it doesn't appear to be so. So that's like one of the things. But it gets very, very technical as we get into these variations, to the point where I'm emailing my theorist friends and saying, I don't understand this paper. Can you explain it to me? All right.
You saw those little hiccups.
Uh-huh.
Do you see those in optical as well? Or do you think
You do see them in optical, but they're much smaller. So you need very precise instruments or thousands of observations to detect them. That's the advantage of the ultraviolet is that it just blows everything up. It's like putting a magnifying glass on the light curve. It just blows every little feature up, so it's much bigger, easier to detect.
Any last question?
Are there different cycles that, other than just like, I guess a build up and a...
There are. It's a very good question. He asked if there's different cycles in that main one of every 12 hours. There are. Some of them go through changes where their amplitudes, how much they pulsate, will shrink and grow over the span of weeks. This is called what we call the Glasgow cycle. It's not really well understood why they do that. About a third of them, I think, do that, where they just gradually over weeks and months change that cycle. There are ones that pulsate in two modes at the same time. They'll do this big oscillation, then a small oscillation, then a big one, then a small one. We're still trying to figure out that. That's one of the things that Swift is going to do, is it's going to map out where those things happen so we can learn better about what is causing those changes in the stars. So very good question.
Let's move on to it.